I want to thank the PyTexas organizers for putting on this conference. I was really looking forward to coming down to Austin to hang out with some friends, talk about Python, and eat some brisket. But unfortunately, that's not in the cards for 2020. Hopefully, we can make it happen next year. And to everybody out there, thank you for tuning into the session. I really appreciate your time. My name is Aly Sivji. You can find me on Twitter. I am at @KaiaSivjis. I'm one of the organizers of the Chicago Python users group. We call ourselves ChiPy. ChiPy is one of the largest Python communities in the world. We have over 6,000 members, and every month, we usually hold 3 to 5 events. Normally at this time, I'd invite you all to come out to Chicago and attend a ChiPy event, but we've had to cancel all of our in-person meetups until it's safe to meet in large groups. But we have been engaging our community through various online platforms. We recently started live streaming our events to our YouTube channel. Now you don't actually need to come out to Chicago to attend a ChiPy event. You can do it from the comforts of your own home. Check out our channel, subscribe to it, hit that bell icon, and you'll get notified of all of our upcoming live streams. Hope to see you all there. Let's get started. So this talk is titled Everyday Design Patterns, and I really wanted to emphasize that we don't have to be designing complex distributed systems to implement design patterns. We can go ahead and use them in our everyday code. So I want to start off by sharing an experience of how the Facade pattern made my code easy to change. In the Chicago Python Slack, we have a bot that displays a list of our upcoming events every time we use the /busybeaver events command. Like most user groups, Chicago Python leverages the Meetup platform to publicize our events. And our Slack bot uses the Meetup API to fetch a list of upcoming events. In August of last year, Meetup announced that they're going to remove version 2 of their API, and they're going to require all clients to migrate to version 3. This wasn't a problem. I was using a Python API client. I probably just had to go out and update this client. I'm going to go ahead and probably change a few calls, and I'd be good to go. Unfortunately, the project I was using was in maintenance mode. So what does this really mean? Looking at the documentation, it doesn't seem like there's much support for the version 3 API. So we're going to have to roll up our sleeves and do things the old-fashioned way. That is, we're going to have to use requests. We're going to hit that Meetup API. We're going to parse the resulting JSON. Usually this means that we're going to have to go out and update integration code across our project. Fortunately, I had used the Facade pattern when designing this integration. In this image, you can see a diff for all the changes that are required to change the Meetup integration from version 2 to version 3. I only had to change this one class. Then I updated all my contract tests, and I was done. All the code that leveraged this meetup.com integration, it worked the same as before. The Facade pattern's pretty awesome, but we're getting a bit ahead of ourselves. Let's talk about design patterns. Design patterns are solutions to commonly occurring problems in software design. We can think of design patterns as customizable blueprints that can be used to implement a solution to a known problem. When we use a pattern, we're going to need to adapt it to our specific use case or the specific needs for our project. There are many benefits of using design patterns. Design patterns are tried and tested solutions to commonly occurring problems in software design. Design patterns are not specific to any one domain or any one application area. Design patterns make our code reusable. We can extract the functionality we need and use it in a separate project. And design patterns, they give us a shared vocabulary with other developers, and this is really important. Once we have a vocabulary, we can communicate with other developers. Common language, it elevates the way we think. We can talk about architecture by talking about high-level abstractions without focusing on low-level details. I wouldn't be giving the full picture if I didn't talk about some of the criticisms of design patterns. Design patterns are considered workarounds for the limitations of a programming language. For example, in Java, there's design patterns that mimic the behavior of language features like multiple inheritance and decorators. Languages like Python have these features built into the language. Always relying on design patterns without thinking about the larger picture, it can lead us to design inefficient solutions that have many levels of unnecessary hierarchy. And finally, as programmers, we have a tendency to solve a problem using the latest and greatest thing that we just learned about. Design patterns are great, but they're not a holy grail. We're going to need to understand how to use them properly. I find a lot of talks on design patterns, they try to cover way too many patterns, so I'm going to do the exact opposite. In this talk, we're only going to be talking about a single pattern, and that pattern, unsurprisingly, is the facade pattern. So imagine we have a home theater system that has a bunch of different components. Say we got a TV, a cable box, a Blu-ray player, a receiver, and a bunch of others. Each of these pieces of equipment, they have their own remote, and we can use each of these remotes to turn on and interact with each of these components. Or we can program an all-in-one remote. And this remote, it has a simple interface. If we want to go out and just watch TV, we can click a button, and we can program that button to turn on our TV and turn on our cable box. If we want to watch a Blu-ray or a DVD, we can program the remote to turn on our TV and turn on our Blu-ray player. This all-in-one remote, it provides a simple interface to all of our components of that home theater system. This is the class diagram of a facade pattern. Here we can see that we have multiple clients interacting with a complex subsystem through a facade. The facade pattern has many benefits. It simplifies the interface to a library, a framework, or a complex set of classes. If the user requires some lower level functionality, they can bypass the facade and interact with whatever class they need to as required. But for most clients, having a facade is going to be a good enough interface. The facade pattern also reduces the number of things that our client needs to know about. The facade pattern promotes weak coupling between our subsystem and our clients. If the underlying subsystem changes, we can go ahead and change our facade, and our clients, they wouldn't know any different. The facade pattern, it provides us a way to define layers in our software architecture, and as a side effect, we can stub out each of these boundaries and simplify our testing. We're going to come back to that a little bit later. And finally, we can use the facade pattern to break apart a monolith. We do this by keeping our original functionality, but we place that functionality behind a facade, and then we start rewriting our client logic to deal with this facade. And then whenever we're ready to make the switch, we can replace the facade's method calls with calls out to another service via an API or a queue. Let's explore the facade pattern with a case study. Normally, when I cut a new version of software that I own, I include a changelog that describes the changes that I made since that last release. Here's an example changelog. We can see that there's a list of changes with links to the relevant pull requests. I generate these changelogs manually, and that's not really a lot of fun, so let's think about how we can write a script to automate that process. This project, it's on GitHub. The master branch is protected, so any changes that need to be made, they can only be made via a pull request. I also squash all of the commits before I make a merge into master. This makes generating a changelog pretty straightforward. We start off by getting the last published at date of the release that we care about. We grab all the commits since that date. And finally, we're going to get all the commit messages and then generate a changelog. Fortunately, we can use the GitHub API to get this kind of information. So let's write up some code to generate a changelog. Our function, it's going to take in 3 parameters. We have owner, we have repo, we have function, or so we have version. And then we're going to use the request library to hit up the GitHub API. We're going to find out when that release was published. If this version exists, we're going to extract the date time string and return it. If not, we're going to raise an exception. Next, we're going to use the GitHub API to find all commit messages since that last version was published. And finally, we're going to return the commit messages in chronological order. We're going to have the earliest message all the way to the latest message. Now let's start thinking about how can we test the script we just wrote. Our current workflow, it looks like this. We're going to make some kind of HTTP requests to the GitHub API. We're going to get some responses back. And when we're testing, we really don't want to be depending on this external system. If GitHub goes down, we're not really going to be able to get any work done, and that doesn't make a lot of sense. This is why when we go out and write our tests, we want to replace GitHub with a stub that returns canned responses. This enables us to write tests without GitHub, and we can make our tests deterministic. So let's take a look at our test function. We're going to use a package called responses to stub out calls to our API. And the way this library works is we're going to specify canned responses for a given URL when it's hit with a given HTTP verb. Next, we're going to run this function that we want to test. And then finally, we're going to confirm that our function returns the values we expect to see. But we have one problem. Directly integrating third-party libraries or third-party APIs into our business logic, it couples our code to something we don't control. If the thing we depend upon changes, we're going to have to rewrite our business logic as well as go out and rewrite our tests to make sure things work as expected. Our current approach has a few limitations in addition to this tight coupling. Our code, it currently only works for public repositories. We're going to need to use a GitHub access token with the correct privileges to authenticate ourselves if we want to ever access private repos. We can probably also make better use of the request library. Specifically, we can be using the sessions feature as well as explicitly setting headers. Also, when we directly integrate integration code into our business logic, it means that our business logic has to be intelligent. It needs to know about things like error checking for HTTP errors or for exceptions. It also needs to know about things like retry logic, JSON processing logic. Earlier, we used a function to fetch a list of commits. This time, we want to hide our implementation. We want to keep track of internal state. And we also want to implement some additional logic on top of this. This seems like the perfect opportunity to use a class. So let's take a step back and talk about object-oriented programming in Python. So object-oriented programming is a paradigm that's based around objects. We try to model real-world things as objects. And when we design a solution, it involves a collection of collaborating objects that communicate with each other by sending messages. objects have data along with behavior. And object-oriented programming allows us to think at a higher level. We can create objects with set data and set behavior, and then we can perform actions on those objects to accomplish the task we're trying to do, versus telling the computer to do things in a sequential, linear manner. In object-oriented programming, we have classes and we have objects. A class, that's a template that allows us to create objects. We can also say that we created an instance of an object from a class. I really like this cookie cutter analogy. The cookie cutter is like a class, and each cookie is an instance of a class, like an object. Object-oriented programming has 4 main principles. There's encapsulation, there's abstraction, there's inheritance, and then there's polymorphism. For the problem that we're solving with the facade pattern, we're only going to be leveraging encapsulation and abstraction, so let's just focus in on those. Let's start with encapsulation. Encapsulation bundles data and behavior into a single logical unit, and we call that unit an object. Encapsulation is used to hide the internal representation of an object. Capsule pills are a great form of encapsulation. They hide the active ingredient and excipients inside of a gelling agent. Python doesn't really have any kind of methods built into the language to enforce encapsulation, but we do have some conventions that allow us to know how data can be accessed and how functions should be called. Instance variables and functions, they can be public, and this means they can just be used by everybody. Protected variables and functions start with a single underscore. These elements, they're not going to be part of a class's public interface. Python has a philosophy that we're all consenting adults. So if you want to go ahead and use protected variables, there's nothing out there stopping you. In fact, it actually might be the right way to solve the problem that you're trying to solve. But just don't be surprised if this interface does change later on. It's something that's not guaranteed. And then we also have private variables and private functions, and these begin with 2 underscores. And when the Python interpreter sees a private attribute, it performs a type of name mangling to make sure that these attributes are hidden. These items still can be accessed since this name mangling is pretty deterministic, or it is actually deterministic, but this kind of practice, it's really highly discouraged. Remember, encapsulation is about information hiding. Next, let's discuss abstraction. With abstraction, we're able to hide the complexity of our internal implementation inside of an object. It's also recommended that when objects communicate with each other, they do so by calling each other's public methods. Abstraction, it hides complexity. It also lets us isolate the impact of changes. We can go ahead and change the internal implementation without changing the calling code. Cars, those are complex systems with many moving parts. But in order to drive a car, you really don't have to understand how a car works. You just need to be able to use the interface. And for a car, this would be a steering wheel, an accelerator, and a brake. It's the same for Python. If we're given a class, we really don't care about the underlying implementation. The interface is the only thing that matters to us. The interface, that's exactly how we interact with this object. Remember, abstraction is about hiding our implementation. And just one more time, encapsulation is about information hiding. Abstraction is about implementation hiding. Now that we have a bit more context, let's take a look at how we can use a class to wrap our GitHub integration. Let's set some guidelines for the acceptance criteria for our MVP. We want to use request.sessions to improve performance. Let's also use HTTP basic auth with a GitHub access token so we can access private repos. We're going to want to set some HTTP headers, be a good citizen of the web. It would be great if this class had some code to handle errors. And if this class can also handle JSON parsing, this abstraction, it would be pretty complete. This is a high-level overview of what we're really trying to do. We're going to have a GitHub client that we initialize with a token, and then we can call functions on this client and get back the information that we requested. So we'll start by creating a GitHub client class. This takes in an OAuth token. We set some headers. We create a session and save that to an instance variable. And this session, this class has a function get release date, and this is going to get the release date for a given version. And so this function is going to take in some parameters. We're going to construct a URL. We're going to hit that URL with the request sessions that we just stored in the instance variable. If the version doesn't exist, we're going to raise an exception. Otherwise, we're going to extract the data that we need from this JSON blob that we just got back, and then we're going to return that back to our caller. This class, it also has another function, and this is called getCommitMessages. It's going to get all the commit messages from a given date. So the function is going to take some parameters. We're going to construct a URL. We're going to hit that URL with the session that we stored in the instance variable. We're going to raise an exception if the status code's not within an acceptable range. And finally, we're going to extract the items from that we need from our JSON blob, and then we're going to return that information back to our caller. To create a changelog, we're going to need to create one additional function. I usually call this function a driver function. It's going to run our class that we just wrote. We're going to create an instance of a GitHub client. We're going to pass in our API token when we initialize it. We're going to grab the release date, save that to a variable, and then we're going to go ahead and grab the commits from that last release. Now let's take a look at how we can go ahead and test this changelog we just wrote. Like before, we're going to use the responses library to stub out the GitHub API when we go ahead and test. Here's the code to test the getReleaseDate function. And here's the slide. And in this slide, we're going to be testing our getCommitMessages function. This implementation, it has a driver function. This is code that's going to be used, so we have to find a way we can test this as well. And we're going to do this by creating a GitHub client stub that's going to return canned responses. And this enables us to write simple unit tests for this for this generate changelog driver function. Now we can go ahead and monkey patch our GitHub client with the stub we just created above. And we can ensure our function works as expected. Note that in this test, we replaced our boundary with a known value. Instead of replacing our external boundary with like the GitHub boundary with like a stub, we replaced something inside of our system with a stub. And so wrapping these third-party integrations, you saw it requires a little bit of extra work. Like we have to write a driver function, go ahead and test that driver function. What are some of the benefits of using this approach? Libraries, they're general purpose tools. They're meant to be used by many different types of people for many different types of projects. We're going to provide a simple interface that only does the things that we need. So we're taking this giant library and we're reducing it to only the things that we care about. This makes our code a little bit easier to test. Another benefit is that our code is loosely coupled. Business logic and integration logic, they can interact with each other, but they don't have any sense of how each other is implemented. This allows us to build flexible systems, and we can minimize the number of interdependencies between all of our objects. And here we used a class to encapsulate parts of our code that change from parts of our code that stay the same. If this GitHub API, it ever changes, we can go ahead and update our GitHub integration code without having to go ahead and change our business logic or the tests related to our business logic. And this pattern, as we talked about, it simplifies testing. We can replace external boundaries with a stub. There's a fantastic talk about this by Gary Bernhardt from PyCon 2013. It's a fairly old talk, but the concepts that Gary talks about, they're priceless. And if this kind of way of coding looks familiar to you, that's because it's part of software architecture methodologies such as hexagonal architecture, also known as ports and adapters, and clean architecture. The idea behind both of these methodologies is that we want to create loosely coupled components, and then we want to connect these components using a series of adapters or a series of wrappers. And doing this, it's going to make our code easy to replace and easy to test. And that's the key point. We want our code to be able to change. Software is rarely static. When requirements change, we have to go and update our code to make sure it works for what we're trying to do now versus what we were trying to do before. So going back to our GitHub changelog example, our boss comes back to us. He absolutely loves what we did, but he wants us to use the GitHub GraphQL library. So let's briefly talk about what GraphQL is so we understand the context of the change that we're going to need to make. GraphQL is going to provide us with an API endpoint that accepts queries. And their backend, it's going to resolve the query that it's passed to the requested data elements. And since we're querying data, the server can fetch exactly what the clients ask for. In comparison, when we're using REST APIs, our clients need to go out and make multiple requests, and then we're going to have to piece together that data on the front end or inside of our client. With GraphQL, we can go out and extract the exact data that we want from a single endpoint. So to solidify these concepts, let's work through an example. This is a GraphQL query. Given a repository and a release tag, we want to pull the published at field. These are the variables that we're going to substitute into our query. And this is the result of the query. And it's only the information that we asked for. It's just that one specific field. When we hit the GitHub REST API, we're sent back all this information when we only really care about that one key value pair. Recall, this is our current workflow. We're going to use the GitHub REST client to get the information we want. And to make the requested change that our boss wants us to do, we're going to need to replace this REST client with a GraphQL client. The business logic that makes use of the GitHub client, it doesn't care if it's using a REST API client or a GraphQL client. The calling code treats the integration code like a black box. It knows it can initialize something with a token, it can ask for some sort of information, and get that information it asks for back. Let's walk through the implementation of our GitHub GraphQL client. We're going to start off by creating a class that takes in a token. We're going to initialize a GraphQL session. We're going to save that session to an instance variable. And in our getReleasesDate function, we're going to pass in the same arguments as before. We want exactly that same function signature. We're going to create our query with our known values. We're going to hit the GraphQL endpoint, and then we're going to return the data we're looking for, or we're going to raise an exception. And in the getCommitsMessages function, that also has the same signature as before. Here we're going to create a query with our known variables. We're going to hit the GraphQL endpoint with that query. We're going to raise an exception if there's an error. And finally, we're going to parse the information we got back and return that return all those commit messages back to our caller. So going back to our generate changelog driver function, we don't have to make any changes here. Our business logic, it doesn't care what kind of client it's using. It just cares that the client has the same interface as it had before. Now we're going to go out and update our contract tests, and we're done. We can go ahead and make a pull request and be happy that we used the facade pattern to wrap our GitHub integration. Let's recap. The libraries and frameworks we use, they're general purpose tools that are designed to solve many different types of problems. If we want to design something that solves our specific use case, we're going to have to actually go out and make it ourselves. We can use the facade pattern to provide a simple interface to a complex subsystem. This reduces coupling between our modules, and loosely coupled modules and loosely coupled systems, they're easy to change. And this is because we started a program to interfaces and not to implementations. As a result, our code is easier to test. We can replace our integration boundaries with values and let our architecture do the heavy lifting. Hopefully, by exploring how the facade pattern leverages object-oriented design principles, we can see that the underlying concepts, they're not too complex. They're fairly straightforward. Design patterns aren't scary. Go out, learn a pattern, implement it in the language of your choice, preferably Python. Discover the benefits of adding more structure to your code. These are all the resources I used coming up with this talk. Thanks everybody for your time. Before I go, I do want to give a shout out to the Chicago Python users group. I would not be where I am without that fantastic organization. Thanks again for your time. My name is Aly Sivji. We'll see you in Austin, hopefully next year.